reactants, the reaction is going to happen faster. If I take my reactants, if I make them less concentrated, it's going to be slower. All right, concentration. Let's say I have a beaker full of
Concentrated dark matter.
exactly what?
What? All I know is concentrated on juice.
Concentrated dark matter. Let's say I've got this much dark matter. Green, that's actually not a bad example for a generic example. If I have concentrated dark matter, the universe disappears a whole lot quicker than if I don't have as much dark matter.
What is that?
All right?
So,
Dark matter just obliterates
oh.
any normal matter. So here we're going to live a lot longer. I don't know about a lot, maybe 5 milliseconds, but we're going to live longer in this beaker
Yeah, of course.
because there's less of it. We're not going to live so long in this beaker. The dark matter. Bad juju. Okay, particle size. Particle size. What cooks faster? If I put peas in a pot to cook, or if I put a full potato, which one's going to cook faster? Which one?
Potato.
No, peas.
Peas.
Potatoes take forever.
Potatoes take forever. It would-
Unless it's mashed potatoes, they don't.
They don't take that long, but that's because you cut them up.
Yeah.
So, the peas are going to cook faster because they have more surface area for that hot water to get around, and the temperature has a smaller distance to go to the center. The potato has less surface area, so less contact with the hot water molecules, or the dark matter, whatever you want to go. There's less contact area.
Like when you cook spaghetti.
So, like which cooks faster, regular sized spaghetti or angel hair? Angel hair, more surface area. The particle size of angel hair is smaller. Smaller.
How big is it?
It's like smaller than spaghetti.
It's like,
Exactly.
exactly.
It's like skinnier. It's like really thin.
Alright,
Very
I'll bring in some angel hair tomorrow and some regular spaghetti. We will measure.
For real.
Green.
Alright.
Green, we will find out the answer to that
Alright.
tomorrow. Alright, here's the example. We watched the fireworks, Dirty Jobs, making the fireworks the other week. So they made these things blow up by adding aluminum powder to them, which is actually very explosive. And why not just put an aluminum bar in those shells?
It's gonna take longer.
Yeah, it's not even, you can't blow, it won't blow up. It's just gonna fall and hit you in the head. And the reason this is flammable, but the aluminum bar, or aluminum foil even, is because of particle size. You get this stuff very, very small, it's explosive. Greater surface area. And then finally, we're going to talk about catalyst, and we have a very short PowerPoint we'll probably do tomorrow on catalyst. And how are we doing? We're doing good on time? All right. We've spoken of reversible and irreversible reactions. Reversible and irreversible reactions. So we know that some, depending on if they have a single arrow, if the single arrow adds irreversible. If there's a second arrow going backwards, then that becomes, although that doesn't, but if you get the second arrow, you've got a reversible reaction. And here's the example of those. And everyone circle this reaction here.
Uh-oh. it's gonna be on test.
It will be on the test. It will be on the test. This is called, something called the Haber process. The Haber process. And this was invented early in the 20th century, I don't know, 1908, late 1800s. Because once we learned how to make ammonia, is NH3, once we could sense, we learned to make two things. We learned to make fertilizer, so we all eat a whole lot better, and we learned to make very powerful explosives.
Oh, yeah.
Explosives. So we'll go down and see Mr. Harris, talk to him about World War I. Very much the result of the Haber process. But these, in this column, these are all reversible reactions. Once they hit a steady state, something called equilibrium, then they can change back and forth. They can, without a whole lot of difficulty, the nitric oxide can go back and become nitrogen and oxygen. With a little pressure on that left-hand side, we can force it this way. So chemicals that are in equilibrium move back and forth. They are not steady state. And which takes us to something called Le Chatelier's principle.
You know, I think we should say process.
I love process.
Oh my gosh,
Process.
not process.
Actually, oddly enough, that bugs my wife to no end when I say process.
Yes, oh my process.
Yes,
Wait, do you say data or data?
Data.
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 Who says data?
Mature,
Ran that.
Oh my gosh.
Data.
Wait,
Hey,
Data.
I hate people who say mature.
Oh my gosh, me too. Mature.
Water.
You know, that's old school.
Water. Water. All right, so seeing the time, I have a little bit of good news. Tomorrow's quiz for 7 and 8, I'm pushing to Tuesday because we're not going to have enough time to do the exercise for Le Chatelier's principle, and we need to do that before Friday's test. So everybody got that? Now, that does not mean that third period is not still going to have theirs tomorrow, okay?
Yeah.
Okay.
This class is not going to.
Okay.
Alright.
Alright, now, that doesn't mean that I will defer them to Tuesday too, so, anyway.
Okay.
You guys.
Don't say a word, y'all.
Alright. So Le Chatelier's principle, a Frenchman. You guys have to know this. Circle this, star this, star this. In these reversible reactions, if I put either stress on the, let's go back. If I put stress, some sort of stress on this side, the reactant side, I can force it this direction. I can make more ammonia. If I put some stress on the ammonia side, by taking out ammonia or putting in ammonia, I can force it this direction. So that's a snapshot of Le Chatelier's principle. If stress is added to a system, meaning I change something on either side of the reaction, then the system will react to relieve that stress. It's going to shift one way or the other. But this is only for reversible. Only for reversible reactions. Only that kind, not this kind. Le Chatelier does not apply to this kind. Stresses. Changing concentration. If I add more dark matter or take dark matter out of that beaker. Changes in temperature and changes in pressure. So these are the three main things that I can change. Let's talk about those for a moment. Concentration. Concentration. Alright, so I have basically a synthesis reaction, A plus B making C plus D. If I put more stuff in on this side, I'm gonna make more products. That's kind of intuitive. If I take some of these out, if I were to take some C and D out, what's left over here in the beaker of dark matter is going to make more C and D. It's going to try and replace it. Yeah, isn't that interesting?
Wait, so.
Wait, what?
I'll
You're
go for it.
Rewind.
Okay, rewind,
Oh, no,
rewind.
oh, erasing, okay.
You
We're
said, so
rewinding.
if you add more stuff on that side, that is gonna be more on that side?
Alright, so yeah, let's start step by step. Let's say, alright, so it's in equilibrium. It's happy. It's in a yoga pose. But I add some more A to it. Giving it some more A, and especially if I gave it more B, but I could do one or the other, I'm going to make more C and D.
So it's
All right.
always just trying to balance itself out.
Yes, it's always trying to balance itself out
Okay.
to whatever this equilibrium that it
So
likes.
why do you say if that goes down, that goes back up?
Alright, so
That's
it's in equilibrium. It's in equilibrium.
like shutting back the rest.
We're back at equilibrium. It's happy, but okay, I'm making something. Product. I want to take some of this. I'm going to take some of this out. That gives more room for these to keep combining.
Wow.
Because I created a void, right? I created a void. I had, this is where I really should have two colors. I pulled this guy out. Pulled 25% out. These say, oh, I got a void.
Ooh.
I've got a void. Let's fill that back in. Yeah, let's fill that back in. So for a while it will do that until there's just not enough reactants to do that.
So they're happy where it's unbalanced.
When it gets unbalanced. This is equilibrium, it's happy,